we can use the Biot-Savart law to look at the magnetic field produced by a moving point charge, and we'll see that it has to be moving, but if it's not moving, it doesn't produce a magnetic field, and so the formula will be hold in general. Uh, what I want to do is I want to look at a charge Q here that's moving in this direction, and in an infinitesimal amount of time, it moves in the direction of the velocity distance dl vector. You can think of this as producing a little infinitesimal amount of current here in this direction. And the velocity, in this case, if it moved dl vector in time dt, the velocity is just dl vector dt, the displacement divided by the time. And now then, for us, we're going to be thinking of a very small charge, maybe an electron, although I'm treating it as positive here. It really doesn't matter. The dq is now then just going to be the charge on this particle. And if you look at the expression I dl vector in the Biot-Savart law, then I could write that as I dl vector, and I is dq dt, and dl vector, so I can move the dt from underneath the dq to underneath the dl vector. Should have a vector sign over that. And then finally recognize that this is just the velocity vector. And so I get that I dl vector could be substituted dq v vector, the velocity vector, into the Biot-Savart law. And so for I dl, in the case of a point charge, it simply becomes, well, here I've done it again. I've got dq dt, that's the current, dl vector, and now then move this dt underneath the dl, and that's just the velocity vector. And so I get dB is equal to mu naught 4 pi dq, the velocity of the charge crossed into r hat over r squared in the Biot-Savart law. Well, so long as dq is small, that's going to hold, and so I'm now thinking of this dq as just a point charge, which would have something on the order of 10 to the minus 19th coulomb, so a very small amount of charge. And then I get the magnetic field produced by a moving point charge, moving with velocity v, and I'm going, if you look at the way I've got this, instantaneously this is the vector r vector, the point where I want the magnetic field produced by this charge. And so it's the distance I am away from it squared in the r hat direction, b crossed in the r hat direction. Now if you look at that formula, obviously if the charge is not moving, if it's static, then there's no velocity, and so there's no magnetic field. Also, because of the nature of the cross product, if r vector, I go out here so that the charge is coming right out at me, r is over here someplace, r vector, then the velocity vector and r hat are parallel, and so again the cross product of parallel vectors is zero, so I get no magnetic field there as well. You get the most field when you've got when it's perpendicular, instantaneously perpendicular to it. But in any event, sometimes it's useful to have that expression. For us, the main purpose is it really points out the analogy between the two, the electric field of a point charge Q and the magnetic field produced by that same point charge if it's moving with velocity v. Again, we've got a fundamental constant, a little bit different in both cases. We've got a point charge, but now it's the velocity crossed into r hat, and and that's the changes of angles is one of the things that sort of makes it a little more difficult to do with magnetic fields.